Hello, welcome to this video on identifying the spanning set of a set of vectors. And more specifically, we're going to be identifying the spanning set of a subspace of a vector space, which, a subspace of a vector space is a set of vectors from that vector space. Just wanted to clarify the title of the video a little more. All right, so I'm going to first start off by identifying or defining what does it mean for a set to be a spanning set of a set of vectors, or a spanning set of a subspace of a vector space. And then I'm going to go over several examples where I'm given a subspace, some set W, that is a subspace of a vector space, whether it be R2 or R3. Again, I'm only going to work in R2 and R3 in most of these videos right now. But this would apply to general vector spaces, right? So you can apply everything you see here to more general vector spaces as well. And yeah, well, I'll be working through examples where I'm given a subspace of a vector space, and I'm asked to find a set that spans that subspace, or a spanning set for that space. All right, so let's begin with some definitions here. So spanning sets. So suppose we're given a subspace W of a vector space V. Now remember what it means. I'm assuming that you know some things from either previous videos of mine you've seen, or other videos somewhere else, or other reading you've done. I'm assuming you know what it means for a set to be a subset of a vector space to be a subspace. Right? That means that it is also a vector space. Okay, satisfies all 10 vector space axioms. If the span of a set S is equal to W, right, this subspace, for some set of vectors called S, then we say that S spans W, or S is a spanning set of W, or for W, or W is spanned by S. Right, all three of these are equivalent statements. They mean the same thing. I'm also assuming here that you remember, and we'll see this later too, when I talk about the span of a set of vectors, right, the span of S, remember that the span of S is the collection of all linear combinations of the vectors of S. Right, so if the set of all linear combinations of the vectors of S is equal to the set W, then we say that S spans W, or S is a spanning set for W, or W is spanned by S. Okay. Alright, so then the rest of the video here is just me going over examples where I'm given a subspace of some vector space, and I'm going to call it W, and we're going to try to find a set S such that W is all linear combinations of those vectors in S, right, is equal to the span of S. Alright, great. So my first example, and again, we're not trying to show that this is a subspace of R2. I'm telling you it is, and you can verify it yourself. Show that W is non-empty, or that it's closed under vector addition, closed under scalar multiplication. You can do all that if you wish. But I'm telling you that this set is a subspace of R2, right? And R2 is a vector space under standard addition and standard scalar multiplication. So W is made up of vectors x1, x2, such that x2 equals 3 times x1, meaning that every vector in W, the second component is 3 times the first component. Alright, so before I like to do this with sets, because a lot of times I find students have a hard time working through certain problems because they don't even understand what kinds of vectors are in a certain set based on descriptions. So before I go into find a spanning set of W, before I go into that, I'm just going to put off to the side here. Here are just some examples of some vectors that would be in W. Right. One of those would be the 0 vector. right? Since, this again, as long as this condition holds, the second component is 3 times the first component, right? As long as this equation is satisfied. If x1 and x2 were both 0, it would be satisfied. So first component 1, and then second component would have to be 3. That's another vector in W. -5, -15 is a vector in W, and so on. And hopefully you can see, again, I'm just putting up a few, just to give you a taste for it, just a few examples of some vectors that would be in W, right? As long as the second component is 3 times the first component. All right. So the question is, can you find what's called, a spanning set of W? Now, another way to state this would be, can we find a set of vectors, which I'll call S, such that, W is equal to the span of the vectors in S. Or, I guess another way to put this, when I say W equals the span of S, that means each vector in W is a linear combination of the vectors in S. Okay. And also every linear combination of vectors in S gives me a vector in W, but that's kind of inherited by the fact that these are all subsets of R2. Right. Okay. Well, hopefully our vectors in S are in W as well, so that way what I just said will work. The linear combinations of vectors in S will be in W. All right, so what we're going to try to do is, can I describe the vectors in W as a linear combination of some vectors, right? So each vector in W, right, every single vector in W looks like this. You have x1, x2, right? But we're given this little equation here. The second component is 3 times the first component. I can replace x2 with 3 times x1. And do you see now how each of these components has the scalar x1? Remember, x1 is any real number. They both have this x1 as a common factor. I pull that scalar out of the vector, and we have x1 times the vector 1, 3. All right. And this is any linear combination, or just scalar multiple, of the vector 1, 3. Right? This is a scalar multiple of 1, 3, a linear combination of the vector 1, 3. Because again, linear combination when there's only one vector is simply a scalar multiple. Right, so a linear combination, scalar multiple, in this case, because there's only one vector, of 1, 3. So that tells me that every single vector in W is just a linear combination of 1, 3, meaning that W equals the span of this set here, the set with 1, 3 in it. All right, and there's the set S that I'm looking for. So the spanning set of W is S equals this set with just the vector 1, 3 in it, right? Because every vector in W is a multiple of the vector 1, 3. So the spanning set of W, can't spell, sorry, wow. So the spanning set of W, which again I'm going to call S, is the set with just the vector 1, 3 in it. Great. Right. And again, you can take a look. I mean, this is just a few examples, but this is a multiple of 1, 3, right? It's 0 times 1, 3. This is obviously a multiple of 1, 3. It's just 1 times 1, 3. This is negative 5 times 1, 3, right? Every vector in W is a linear combination of this vector, a scalar multiple of this vector. So this is, the spanning set, or a spanning set for W, right? Because, you could also say every vector in here is a multiple of 2, 6, because if you're a multiple of 1, 3, you're also some scalar multiple of 2, 6. So, the spanning sets are not unique, right? This is just, I'll say, a spanning set of W, not the spanning set, right? Great, I hope that made sense. I'm going to do the same with the, I've got 3 more examples here. One more in R2. And a couple in R3. All right. So here, we've got the set W is made up of vectors, x1, x2 belonging to R2, such that the sum of the two components is 0. Right? And it's, you can show this yourself if you want. I'm not going to show it here, but this set of vectors is a subspace of R2. You can prove that on your own. All right, so find a spanning set of W, right? Again, find a set, S, a set of vectors such that W is equal to the span of that set, meaning that every vector in W is a linear combination of the vectors in the set S, the spanning set S. All right, so as I did last time, before I get into actually finding that spanning set, I'm just going to put some examples of vectors that would actually be in W. Now, obviously 0 plus 0 is 0, so x1 equals 0, x2 equals 0, the 0 vectors in W. And really, kind of like in the last example, I can look at this equation here, x1 plus x2 equals 0, and solve for one of the variables. Say x1 needs to be equal to the opposite of x2. So really, every vector in W, the first component and second component just need to be opposites. Right? So 1, negative 1, is in W. 3, negative 3 is in W. Negative 7, 7 is in W, and so on. Right? I could think of a million different examples. But just to give you a feel, again, for what vectors are actually in this set called W. All right, so now let's see if we can take a vector in W. All right, so each vector in W looks like this. Each vector in W looks like this. You have x1 component, x2 component, but there's a special relationship, right? And we pointed it out here that x1 plus x2 must be equal to 0, or in other words, x1 must be the opposite of x2. So I'm going to replace x1 with that, the opposite of x2. And x2 down here. And as before, you see how both of these have that scalar x2 in common. Pull that scalar out. And then I have x2 times the vector negative 1, 1. All right, so can you see how every vector in W is a linear combination, right, or just a scalar multiple because it's only one vector, but I keep writing linear combination, or a linear combo of the vector negative 1, 1. Right, every vector in W is like this. Every vector in W is a linear combination of the vector negative 1, 1. So this set of vectors, just the set of vectors with negative 1, 1 in it, is a spanning set for W. right? In other words, the span of this vector negative 1, 1 equals W, right? Because again, W has all linear combinations of negative 1, 1. Now again, this is just a spanning set. You could really take any multiple of this, how about 1, negative 1? What if I said x2 is the opposite of x1 instead? Then I would have it as multiples of 1, negative 1 instead. So it's not it's not the spanning set, it's a spanning set for W. Great. All right, then my next example, I'm working in R3. R3. So here I'm given set W is made up of vectors that look like this, where you have a first component x1, a second component x2, and the third component is 0 all the time. And these are vectors in R3, and this set W is a subspace of R3, and you can verify that on your own. Not doing that. Right. And just as I've been doing, I'm going to show here are just some examples of vectors that would be in W. So again, obviously the 0 vector is in there, right? If x1 were 0 and x2 were 0, and the third component always has to be 0, that's in there. You just let x1 and x2 be whatever you want, right? There are no conditions. The only condition is that the third component needs to be 0. So 1, 5, 0, negative 7, 8, 0, and so on. As long as that third component is 0, you have a vector in W. Okay. All right, as before, we're asked to do the same thing. Find a spanning set for W. So basically, I'm going to find a set S, right? I'm going to find a set of vectors such that every vector in W is a linear combination of those vectors in S. Right. So let's do that. Let's take what does every vector in W look like, right? Each vector in W looks like this. x1, x2, and 0 for the third component. Now remember how for the last two examples, there was some equation involved where I could replace one of these variables with another expression involving just one variable, and then I pulled that out and all this. Well, that's not happening here, right? There are two variables here that I can choose any value for, right? In the last one, right, in the last couple examples, there was only one variable that I could choose a value for, and then the other one had to be fixed, right? For the last example, x1 had to be the opposite of x2, or x2 had to be the opposite of x1. So if you picked a value for one of the variables, you knew what the other one was going to be, right? You couldn't pick both freely. So here you have what are called two free variables, right? You can choose these to be whatever values you wish, right? Two free variables. And you've seen free variables probably before, right? You can, if I say they're free, that means they can be any value, any real number you want. And off to the side here, I'm going to put a little special note for you. You'll see that the number of free variables will give you the number of vectors in a spanning set for a subspace. Right? So you notice how in the last two examples there was only one variable I could really choose, and then I knew the value of the other one. There was one free variable. And did you notice how every spanning set for those last two examples only had one vector? So the number of free variables will be equal to the number of vectors in a spanning set. Now technically that's not totally true, because once I have a spanning set, I could add, any other linear combination on and throw more vectors onto the spanning set. I'll say the number of free variables equals the minimal number of vectors in the spanning set to be more precise. Because again, because like I said, more vectors could be added on and it'd be fine, as long as those new vectors that are added on are linear combinations of the other ones. Okay, so I have two free variables, so that means I'm going to be, for my minimal spanning set here, I'm going to be hopefully finding two vectors. So hopefully this makes sense to you, right? I'm going to split these up so that I have vector involving x1 and a vector involving x2. I'm going to separate my free variables. So x1, x2, 0, isn't this the same thing as x1, and then there's no x1 in this, and then no x1, and then 0 in that, plus, and then the vector with x, all the x2 terms. There's no x2 in the first component, then 1x2 in the second component, and then 0 in the third component. See that little split, and hopefully this makes sense. These are equal, right? And then in this first component, this first vector, each component, I can factor out a scalar x1. I pull x1 out, and then what I'm left with is the vector 1, 0, 0. Plus, and then this vector, I pull the scalar x2 out, and I'm left with the vector 0, 1, 0. All right, so do you see that every vector in W, right, every single vector in this subspace, every single vector in W is a linear combination of the vectors 1, 0, 0 and 0, 1, 0. So I got a linear combo of 1, 0, 0 and 0, 1, 0. And there we have it. This set of vectors, the set with these two vectors in it, will be the spanning set for W. And I'll write that on the next page. All right, since every vector in W can be written as a linear combination of those two, then we would say that S equals the set with vectors 1, 0, 0 and 0, 1, 0 is a spanning set for W. Like I said, it's a spanning set, not the spanning set, because you could just I could have any multiple of this in there instead, 3, 0, 0, and I could put a multiple of this 0, 5, 0, and that would be a spanning set. I could also add another vector, as long as it's a linear combination of these two, right? Because remember, I want every set and every vector in W to be a linear combination of the vectors in S. So if I throw on a third vector, say that was the sum of these two, a linear combination of these two, say 1, 1, 0, that would be totally fine. That would also be a spanning set. So just be careful with that. Just know that what I set up here matters. The number of free variables is the minimal number of vectors in a spanning set, because you could again add on vectors that were linear combinations of these two, and you'd still have another spanning set. It just wouldn't be minimized, right? It wouldn't have a minimal number of vectors in it. Okay, and another way of saying this, remember, is that W must be then equal to the span of S. Right, that's what that means. It means every vector in W is a linear combination of the vectors, these two vectors. Great. All right, then my final example has another one of those equations coming up. All right. So W equals, a set of all the vectors from R3, you have x1, x2, and x3, but there's a condition. 3 times the first component minus the second component plus 4 times the third component must be equal to 0. All right. So remember solving equations or solving systems and stuff, how many free variables do I have in this, right, in this equation here? In this equation, I can't let x1, x2, and x3 be any numbers I want. I can't have this be 5 and this be 100 and this be 17, because that's not going to be equal to 0. It's not going to be satisfied. You see, I have a, if I put this in, like a matrix form, it would be a 1 by 4 matrix. So when you put it in reduced row echelon form, you'd have a lead 1 if you, multiply everything by a third. And then the other two columns for x2 and x3 would not be pivot columns, right? Wouldn't have a lead 1 in it. So this has two free variables. I could let x2 and x3 be anything I want. But then, if I let x2 be 7 and x3 be 1, then I know x1 would have to be 1, right? You can't pick x1 to be whatever you want. So you have two free variables. So again, what's going to happen is the number of vectors, or the minimal number of vectors that's going to be in the spanning set of W that I'm trying to find is going to be 2 vectors. Right. Now I'm just going to call x2 and x3 the free variables, and you can leave them the way you want. You can leave them this way or call them s and t, let them take on expressions that take on any real number. And yeah, so I do like doing that. All right, I don't really particularly care for leaving the variables the way they are. So I'm going to let, for the free variables, I'm going to let x2 be the letter s, where s is any real number. And I'm going to let x3, the other free variable, be the letter t, right? A different letter, because they are different numbers. I can choose them to be wherever I want. Where s and t are real numbers. Okay, any real number you wish. So then that equation looks like this. We have 3x1 minus s plus 4t must be equal to 0. So then x1, okay, must be equal to s minus 4t, all divided by 3, or 1/3 s minus 4/3 t. All right, if you divide each one by 3. I guess I could have called these something else. If I called that 3s and 3t instead, it would make this look a little cleaner. So why don't I do that? All right, I can call this 3s instead and 3t. They'll still be any real number I wish, right? Just pick different values of s and t. So this is now 3s, and this would be 12t, right? 4 times 3t when I replace x3 with that. And then you have 3s here, 12t there, and then that would make this a lot simpler looking. So we'd have x1 equals s minus 4t. All right, just so I don't have fractions. That's the only reason I made those 3s and 3t. All right. So then the solutions of this equation are x1 equals s minus 4t, x2 equals 3s, x3 equals 3t, right, where this isn't the answer, okay? This isn't the answer. I'm just saying these are the solutions to this equation. And I can now show you some examples of vectors that would be in W. All right, so here are some vectors in W. That's the only reason I went about solving this, because the earlier ones, those first couple examples, those equations were really easy to solve. X1 was equal to x2 was equal to 3x1, and x1 plus x2 was equal to 0. Those were really easy to solve, but when there's more variables, it's a little trickier. So here are some examples of vectors that would be in W. And really all I'm doing is changing the values of s and t. Right. Now again, the easy one is the 0 vector. If s were 0 and t were 0, right, that'd be 0 minus 0, 3 times 0, 3 times 0. You have the 0 vector. x1 equals 0, x2 equals 0, x3 equals 0. So that's in W. And it should be because it's a subspace of R3, right? How about if s were 5 and t were 1? If s were 5 and t were 1, this would be 5 minus 4. So x1 would be 1. And if s were 5, x2 would be 15. And t were 1, x3 would be 3. And let's double check. 3 times this minus this plus 4 times this, that'd be 3, minus 15 is negative 12, plus 12 would indeed be 0. That equation would be satisfied. So here's a vector that's in W. Another one, how about simply if s were 0 and t were 1? That'd be negative 4 for x1, 0 for x2, and 3 for x3. All right. And I could do that all day long, right? Just after solving this equation, with setting up my free variables in terms of some parameter s and t, I can find any vector I wish in W, right? Just replace s with any number, t with any number. And this is where I'm going to use here. I'm going to use these expressions here to help me find this spanning set of W. All right. So great. Now I've listed some vectors. You can find all sorts of ones, if you want. But now I'm trying to find a spanning set of W, right? A set of vectors such that every vector in W is just a linear combination of those vectors in what I'll call S. All right. So as I've done with each of these, we're going to take a vector from W. What does that look like? Right. Each vector in W looks like the following. You have x1, x2, x3, but as I mentioned, they have to satisfy, these components have to satisfy this equation, and I showed you that when they satisfy this equation, they'll take on these forms here. So x1 would be equal to, s minus 4t, where s and t are any real number I want. x2 would be 3s, where s is again any real number I want. It's the same s as that one. And x3 is 3 times t, the choice of t I make up there. And I showed you when I let them both be 0, I got 0, 0, 0, and so on. Right? I can let s and t be anything and get all sorts of vectors in W. So every single vector in W looks like this, has this form. All right, and just as before, I have two parameters, right? Two free variables, this s and t. So as I did with the last example, I'm going to split this up into the sum of two vectors, one with the s terms in it. So there's s, 3s, and 0. All right, there's s, 3s, and no s, plus, and then the terms with t in it. There's negative 4t in the first component, 0t in the second component, and 3t in the third component. And then now you can see that I can pull out the scalar, right? I can pull out the value of s, I can pull out the value of t from these. So this is s times then 1, 3, 0, plus, and then pulling t out of these, t times negative 4, 0, 3, and there we go. There's a linear combination of a couple vectors. Right? So what we're seeing in this little line of reasoning here is that every single vector of W, every vector in this set, is a linear combination of the vectors 1, 3, 0 and negative 4, 0, 3. Right? So a linear combo of 1, 3, 0 and negative 4, 0, 3. And these two vectors make up this spanning set of W. All right. So this set S, so S equals the set with 1, 3, 0 and negative 4, 0, 3 is a spanning set of W. And remember what that means. That means that W is equal to the span of this set, right? Every single vector in W is a linear combination of these two. All right, and again, I emphasize one more time, this is a spanning set, not the spanning set. Because I could just, throw in a different multiple of this, maybe 2, 6, 0, or a different multiple of this, negative 12, 0, 9, and that would be a spanning set as well. Because if you're a linear combination of these two, you're also going to be a linear combination of any multiples of these two. And also, I could throw on more vectors as long as they're linear combinations of these, right? So if I were to put on, say, negative 3, 3, 3, which is the sum of these two, I could put negative 3, 3, 3 on here and have a set of 3 vectors that spans W as well. All right, it's just that 2 vectors is the minimal amount. Right, the number of free variables is the minimal number of vectors in a spanning set. You can always add more, but again, as long as they're linear combinations of the vectors in the minimal spanning set, you could add more vectors on and create different spanning sets if you wished. Okay, wonderful. All right, so lots of stuff there, right? Lots of terms and manipulations of equations and whatnot, and But if you're asked to find a spanning set of a subspace, look at what each vector in that subspace looks like. Try to find some general form for it, and see if you can split it up and write it as a linear combination of some vectors. If you can, then you have your spanning set. All right. And you should be able to, right? Because if there should every subspace of a vector space should have some sort of spanning set. All right. Great. All right, and that's all I've got for this video. Plenty of examples there. Have fun practicing this stuff, and thank you very much for watching.